Hello, AP chemistry students. In this lesson, I just wanted to go over some of the highlights from our class today, Wednesday, October 12th. And what we discussed was heat. I gave you a reading in the assignment. I'm just going to go over some highlights of that reading. When we're looking at heat, we want to make sure that we understand that is the transfer of thermal energy. Temperature is the measure of thermal energy within a sample. And so what I've done is I've highlighted some things that you might want to make note of from the text, and then even things that I would even put in my own notes. And I kind of hand wrote those more for my use than for student use. But maybe it will serve as an example of something that you can put in your notes, and how you can kind of pick things from your text to help you when you are reading scientific text. So some of the things I noted was temperature is a measure of thermal energy. I added something I already knew. It's a measure of average kinetic energy. And I just want to bring that up because in AP chemistry, on the test, many times they're going to refer to the average kinetic energy, and they will not say temperature. So they will say these two things have the same average kinetic energy. What they mean is they have the same temperature, but they will not say temperature. They would want you to know that temperature is a measure of average kinetic energy. So I just wrote that in there. And then how do we measure temperature? Well, we know thermometers are used to measure temperature, or you could say they measure thermal energy within a sample. And so heat is the movement of energy. And why would heat move? Well, it moves because of a temperature difference between a system and surroundings, or the temperature difference between two objects. And then so which way would that move? And so if we read our text, we see that heat flows from higher temperature to lower temperature. So if I had a hot cup of coffee, heat is going to flow from my hot cup of coffee to the cooler surroundings. All right. So I have a high temperature coffee and low temperature air, cup, hand. The temperature moves, or the heat moves this direction. Heat moves from the hot to the cold, the higher temperature to the lower temperature. And this air, cup, hand, imagine I'm holding the cup of coffee, probably not too hard to imagine. We would call that the surroundings. All right, and so there we go. That kind of gets us into the realm of heat flow, and then also what temperature is. We also have this idea of thermal equilibrium. The heat transfer from the coffee to the surrounding stops when the two reach the same temperature, and that's what we call thermal equilibrium. So at some point, the coffee and the surroundings become the same temperature, and so there is not a net change in heat. All right, so that doesn't mean things stop moving. It doesn't mean that there's still not a transfer of energy, just there's no net change in that transfer, or no additional heat is added. So, and we'll get back to thermal equilibrium here in just a second in another example. Then another part of the text I wanted you to look at was this heat formula, where we see Q, meaning heat, the unit of heat being capital J joules, is equal to mass in grams, times, you notice this variable here, CS, which means specific heat capacity, and its joules are, and its units are joules per gram degree Celsius. All right, so we see specific heat capacity has these units, joules per gram degree Celsius. Unit of mass, grams. Unit of heat, joules. Unit of temperature, we should be familiar with, is degrees Celsius. All right, so what I have listed here are some common heat capacities of some substances. going from lead all the way to sand. And so then what I have here in my notes is I just did a couple sample calculations. And so in my calculations, I kept mass M at 4 grams and my delta T at 25 degrees Celsius. If you notice, my final temperature is 100 degrees, my initial temperature is 75 degrees, so my delta T is 25. We get delta T from final minus initial. And these values here, let's use yellow, these values here are just made up because I want to compare how the specific heat capacity affects the amount of heat for a temperature change. So we have to keep the mass between the samples identical, and we have to keep the temperature change identical in order to see how the specific heat capacity affects the amount of heat that is needed to make that temperature change. We cannot compare, for instance, um, 500 grams of gold to 5 grams of aluminum. It's obviously going to take more heat to heat up 500 grams of something than 4 grams of something, with even relatively large specific heat capacities. So we have to make sure our variables are accounting for some constants there. 4 grams, 25 degree temperature change. What is the only difference? The specific heat capacity, and then how much heat would be needed to cause that temperature change. So we notice that if we have 4 grams of this gold and we have a 25 degree Celsius temperature change, that it only requires 12.8 joules. But if we wanted to heat up a 4 gram sample of aluminum by 25 degrees, it would take 90.3 joules. So it takes a lot more heat to heat up aluminum than it would be to than it takes to heat up the same mass of gold. And what accounts for this difference? Well, the difference is in this specific heat capacity. We see that gold has a lower specific heat capacity than aluminum. And so what accounts for the difference? Aluminum requires more heat to have the same change in temperature as gold because it has a higher specific heat capacity. And of course, we have to make sure we know that this is when the mass is equal, right? This is when the mass of those two samples are equal. So even if we wanted to cool down aluminum, all right, it was going to take, and we had a negative delta T. Let's say we went from initial temperature of 100 to a final temperature of 25, and this was a negative value for both of those. Well, it would take aluminum losing 90.3 joules of heat in order to have that same temperature change, and it would only take gold losing 12.8 joules. So you can have a negative Q value. A negative Q just simply means that heat is removed from the object. Positive Q means heat is gained by the object. All right, so if heat is removed, it's getting cooler, then your Q is going to be negative. Now, you cannot have a negative amount of energy. So that negative sign is not referring to a negative amount of energy. It's referring to the flow of energy out of something. All right. And the positive would be the flow of energy into something. All right. So if we say negative 12.8 joules that is required for the gold, we mean that it's going to take that the gold would have to lose 12.8 joules of energy to its surroundings, or transfer 12.8 joules of energy to its surroundings in order to have a temperature change of 25 degrees, in order to get cooler. And the same thing with aluminum. It would have to transfer 90.3 joules of its energy to the surroundings in order to have a temperature change. Still requires a larger amount of energy to be transferred in order to have a temperature change than gold, the same temperature change as gold. So just take a look at that, and we'll go over that in your lesson, and hopefully we will be really sound on how to make calculations involving Q. As a matter of fact, I'll go ahead and show a sample question. This is not one from your exact lesson here. Let me get a calculator so we can get this going. Desmos, there we go. And what we have here is it says a 55-gram block initially at 27.5 degrees Celsius absorbs 725 joules of heat. What is the final temperature of the aluminum? And so things that we would want to look at when we do our assignment, and it's very important because some people are not looking at them, and then they're wondering why we're scoring low. Well, I'm telling you how you get your score in the rubric, and it's no secret that most of these assignments have rubrics per question on every question. So what you should show is the equation, and the equation should solve for the unknown variable, and then your calculation should include all units, and those should be plugged into the equation, and then your answer should include the units and should have the correct number of significant figures. All right, should have the correct units and then also the correct number of significant figures. All right, so if we look at this, we know that we're going to be using our heat formula because it says what is the final temperature of aluminum. We know that we're going to use our formula Q equals mass times specific heat capacity, and then times our delta T. You can get your delta over here. Whoops, we got to go back up here. Times delta T. Yeah, there we go. Times delta T. And if we ask ourselves, is this solving for our unknown variable? As according to the rubric, we would have to say no. So if Mr. Schmidt were going to score this, he would say this equation does not solve for the unknown variable. You could either use this equation and break this delta T up within this equation to say TF minus TI, or you can just go ahead and solve for delta T, and then you can use this equation here that that TF, and I want to show you where I'm getting this from before I go too much further, but delta T would be equal to TF and then minus TI. All right, and so if we rearrange that equation, to solve for TF, we would see TF is equal to delta T plus TI. All right, and so we see that, and I wanted to just show you this is how we're getting this equation. So you don't need to show this one, but you do need this one. All right, and I just wanted to show you where you got it from. So between the two of those, we are solving for the unknown variable. So we need to take this equation and solve for delta T. So I'm just going to go ahead and use that, and we're going to say delta T is equal to Q, we're just rearranging algebraically, and then over mass times specific heat capacity. And once again, if you can copy and paste, you should always do that in this calculator feature, because it makes it a little bit easier. And then all we have to do is plug in some values. And so the delta T is going to be equal to Q. Well, what does this say happens? It says the aluminum block absorbs 725 joules. So we know we're going to have 725 joules as our Q. Our mass is 55.0 grams. And we're going to multiply that times our specific heat capacity of aluminum. Now, that's one thing we're going to have to go look at real quick. I guess I didn't put it in this. I put it in your assignment. I put the chart in there. But you can look on your chart because I don't have one readily available. Let me see if I can go to my notes here. Here we go. Here it is. 0.903. So in your assignment, those charts are, I think, in the question already. I just I didn't put it in this example. So 0.903 is what we would have there. And so let's go back in there and plug that in. So 0, whoops, there we go. Let's do that, times 0.903. And what must we have in our calculations? Units. You said it, joules per gram. And then we find degree over here. Another way of getting degree is to hit Alt 248. I don't know if it works in this, but it works in everywhere else. Yeah, there it goes. Alt 248. It's pretty cool. Or you can just hit that degree sign there. So joules per gram degree Celsius, and we can see that we have all our units in there. And then all we need to do is plug that into our calculator. So we have 725 divided by 55, and then we can say times 0.903, and what we get is 14.59. And I'll just go ahead and plug this whole value in there. And this is our temperature change. So what's our unit? Well, we know it's a temperature change, so we should know that it is degrees Celsius, right? And so what we have is 14.59 degrees Celsius. Now, how else would we know it's degrees Celsius? I'm gonna go ahead and shrink this a little bit because it's a little bit too big. How else would we know it's degrees Celsius? Well, we just check our units. And what we know is that we have joules cancel. Ooh, I don't like that. Okay, there we go. And joules. And then we have grams, and grams cancel. And the only unit that we're left with is degrees Celsius, which makes sense because we're solving for temperature. All right, and so there we have that. Now we need to solve for TF. So TF is equal to delta T plus TI. And so when we put an equal sign in an equation, we have to make sure the thing that we're saying next is actually equal. So our delta T is 14.59, all that degrees Celsius. So we'll go ahead and make sure we put in degrees Celsius, and then plus our initial temperature of 27.5 degrees Celsius. All right, plus 27.5 degrees Celsius. Let's see. And what we see there is this becomes, and I'm going to go into my calculator again, and we're going to say plus 27.5. And so we get 42 point all of that. Okay, so that's what we get there. And so we're going to say degrees Celsius. All right, so and Celsius. Okay, so these things are all equal now, without a doubt. Let me go back in here, get that a little bit closer. Not a requirement, but something I would like to do. Now, we have to make sure that we have the correct number of significant figures. Now, technically, in this value here, we could have 3 from the 55.0. That's a trailing 0 with a written decimal. And then we used 725. That's 3 significant figures. So this answer technically should have 3 significant figures. So we would say 14.6 degrees Celsius. And then we see that we are now adding, all right, we're given the value 27.5 degrees Celsius. So we're adding these two things. And when we add significant figures, you go to the same number of decimal places in your answer as the least in the problem. And we see this one has 1 decimal place and this one has 1 decimal place. So our answer can have 1 decimal place. And we notice that when you have 4 decimal places, it's 42.09. So our answer would be 42.1 degrees Celsius. So what I would do is just copy that answer, hit add math, go over to the response, and there we go. So now we have everything that we need. And when Mr. Schmidt checks our work, he goes to his handy dandy rubric and finds a response. Ooh, maybe. Buffering. Okay, there we go. Somebody's recording that right now. Annoying. Let's see if I can find it. Well, if I can't see it in here, I'm not going to spend all day on it. Okay, so maybe that's why it's not in there. Okay, maybe now we can see it. Or maybe not. I think the internet is slow today. So anyway, I'm not going to go over it. We just need to make sure that it follows the rubric. The rubric, did we show the equation solving for the unknown variable? Yeah, we definitely solve for the final temperature. And then I showed you if I'm going to use delta T and I have to solve for that, make sure you're showing that variable as well. So there you go. You got that. Did we use our units? Do we have the correct values with units are plugged into the equation? Well, as far as we know, we have the correct values. We checked them. We had 725, we had 55, we got the 0.903 from the chart. And then we have the 27.5 as our initial. So yeah, it looks like we got all the values in correct. They have the units canceled out. So we're looking pretty good on that. And then lastly, our answer. We rounded to the correct number of significant figures and the units are included in our answer. So we should be good to go with full credit. And that's as simple as that is. If we go to another example, this one says to determine whether shiny gold colored rock is actually gold, a chemistry student decides to measure its heat capacity. She first weighs the rock and finds it has a mass of 4.7 grams. She then finds that upon absorption of 57.2 joules of heat, the temperature of the rock rises from 25 degrees Celsius to 57. And then what we're supposed to do is find the specific heat capacity of that rock and determine whether it is gold. All right. Even if it is or it isn't, our answer needs to be gold. So in order to make sure our answer is gold, we follow the rubric and we should show an equation that solves for the unknown variable. We know that we are going to need our heat equation. And once again, if we go over here to our add math, we can hit Q equals mass times specific heat capacity, and then times the change in temperature. Now, does this solve for the unknown variable? And the answer to that would be no. We need to rearrange this algebraically to solve for specific heat capacity. And so what would that look like? Well, it should look like our equation solving for CS. So CS is equal to our change in temperature. Oh, excuse me, that's not true. Q over our change in temperature, because we're going to divide on both sides, over our change in temperature times what? Our mass. All right. So there we go. So what we did was we divided by mass and change in temperature on both sides, and we end up with this equation. Now this is solving for our specific heat capacity. And so all we have to do is plug in our values, which makes this really easy. So now we have 57.2 joules, and then our change in temperature, we say is 57 and 25. So you could say that is what, 32 degrees Celsius. And you want to make sure that's right. You can just plug that into your handy dandy calculator. 57 minus, I think it said 25, I'm not sure. Yeah, 32 degrees. So there you go, 32 degrees. And so always check if you're not sure. Make sure you're careful on those things. We'll hit Alt 248, and that gives us a degree sign because we're super cool like that. And then we have our mass, and our mass is 4.7 grams. So now all we have to do is plug in that into our calculator and look at our units. We're going to have joules, and grams in degrees Celsius. And guess what? That is the unit of specific heat capacity. So we must have set this up properly. And so we will get our answer, and our answer will have units of joules per gram degree Celsius. All right, and so we'll just plug in our answer here. So we're going to say 57.2 divided by 32 times 4.7. That was our mass, 4.7. All right. And so we get a specific heat capacity of 0.303803. Yeah, 3803. So just do that there. And so now we have our units in there and everything. And the question would be, well, is this gold? I don't know. I don't know. How would I know if it's gold? Well, I go to my handy dandy specific heat capacity chart. And what is the specific heat capacity of gold? 0.128. So if you thought that was gold, you were fooled. That there ain't gold. That's fool's gold. All right. And so it is not consistent with that being gold. So we can see that we did calculate the specific heat capacity of gold. We solved for the unknown variable. We plugged in our numerical values with the correct units, and then we have an answer that has the correct units as well. So if we wanted to put that in the answer box, maybe on this one, if I were to ask you this, you could imagine that I would make you do some type of written response. But since this is an example, we're not making you do that. So this isn't even a question that you have. It's actually an example problem from the text. All right, so let's get back to where we were and our notes. We went through some of those samples there with how to calculate, how to make calculations involving the heat equation. We didn't even solve one where we're solving for heat where we didn't have to rearrange one. So we solved one with specific heat capacity, and we solved another with delta T. I'm sure you can rearrange an equation that solves for heat since it's already given solving for heat. So when we look at thermal energy transfer, and we were talking about this idea of thermal equilibrium, we see that energy or heat goes from either the surroundings to the system or the system to the surroundings. And so what they're showing here is a metal block being placed in some water, and they're saying that this metal block is 55 degrees Celsius and the water is 25 degrees Celsius. And I put in my notes, notice the metal is a higher temperature than the water. So where is heat going to be transferred from where to where? Well, if the metal is higher temperature, we know that the heat is going to be transferred from the metal, which has a higher temperature, to the water, which has a lower temperature. So the delta T of the metal will actually end up negative, and the delta T of the water will end up positive. The water will gain heat, the metal will lose heat. All right, don't pay attention to this Q in this picture here. That is a great equation, but the water is actually gaining heat. It even tells you in the written text that it is. So, what we see here is this is going to occur. Metal is going to lose, water is going to gain until when? Thermal equilibrium is reached, right? The metal loses heat. It has a negative Q. The water, it gains heat. Water gains heat. And so it has a positive Q. All right. And so that's what we would see there. And then we get into this idea of endothermic and exothermic reactions. Okay, so we're getting this idea of endothermic and exothermic reactions, and you need to be familiar with these energy diagrams. and how they and what they look like. We went over these in a previous lecture. And so we see we have energy and reaction progress on our X and Y axes. And we see that this is our starting energy, and these are just a sketch. These aren't quantitative. I'm not showing an actual plot where we have actual values. But it is important to understand that this would be endothermic, and we know that it's endothermic because the enthalpy of the final is greater than enthalpy of the initial, and that means we're going to have a delta H that is positive. You can see the energy at the end of the reaction is greater than the energy at the beginning of the reaction. And this is just your energy of activation. I just put that in there to kind of remind you. You still need to know that, but not as important to know for thermodynamic section. Delta H is where we're living at in this section. All right, so our delta H is positive for an endothermic reaction. And why is that? Because an endothermic reaction does what? Absorbs heat from its surroundings. Notice, if it's absorbing heat, it's going to have more heat at the end than it would at the beginning. Do you see that? And so that is something to look at. If you look at this example here, they're showing a cold pack. This cold pack is actually absorbing heat from the hand or the wrist or whatever it's put that on. So the endothermic reaction is absorbing heat. It feels cold, but what's happening if it's cold? Heat is being transferred into that. All right. So then we have an exothermic reaction. Exothermic reaction, our final temperature is less than our initial temperature, or the final enthalpy is less than our initial enthalpy. And so what happens is we end up with a delta H that is negative. All right, notice delta H negative. That's exothermic. And notice the graph, there's less energy at the end of the reaction than there was at the beginning. All right, and that's the telltale sign that you have an exothermic reaction. Notice the energy at the end is far below, or even just below the initial energy. And that's what you need to know there. And what happens in an exothermic reaction? It gives off heat to its surroundings. All right, so you can think of a fire. It gives off heat to its surroundings. Anything that is burned is giving off heat to its surroundings. And so if I were going to make some notes, the summary of enthalpy is a pretty good thing to be looking at. Endothermic reaction has a positive delta H. Why? Because it has more energy at the end. Why? Because it's gaining energy from its surroundings. All right. And what else do you know about it? It feels cold to the touch. What was an example of that? That ice pack, right? And then an exothermic has a negative delta H, has less energy at the end than it did at the beginning. And why would it have less energy? Well, because it gives off heat to its surroundings and it feels warm to the touch. So it's giving off heat, it's going to feel warm. All right, and so just be aware of that. Now, I put this in here because some of these are maybe a little anti-intuitive, but I just want you to think about heat transfer as we go through these. If we've got sweat evaporating from the skin, in order for anything to evaporate, where must heat go? So if we think of sweat as our system, the sweat is going to gain heat. Where is it gaining heat from? The skin. So we are warm, we sweat, and that sweat absorbs heat from our body, and that body heat is absorbed into the sweat, and then eventually the sweat evaporates, right? And that heat leaves our body, and we feel cooler, all right? But the sweat is gaining heat. Do we see that? Sweat is evaporating, it's gaining heat. That's going to be an endothermic reaction, right? The sweat is gaining heat in order to evaporate. When we have water freezing in a freezer, in order for something to freeze, this is going the opposite direction. Now we have liquid water, and we're going to make it solid water. In order for that to happen, you know this, that water is going to have to get cooler. How does it get cooler? It transfers its heat to the freezer. And so then the water becomes cooler. So that would be an exothermic reaction. All right. And that's anti-intuitive because you're saying, well, that doesn't feel warm to the touch. Well, in this case, we're still having to think about the transfer of heat. All right. And if it's losing heat, well, then it must be exothermic. And the only way water is going to freeze is if it loses heat. And then lastly, we have the burning of wood in a fire. And when I told you anything that is burnt is going to be exothermic reaction. And so just be aware of that. And then the last part that we have here is stoichiometry, your favorite topic, couldn't leave it out. Stoichiometry, also the enthalpy of a reaction, heat of a reaction, delta H of the reaction, that just tells us how much energy is gained or lost within a reaction. And then we can use stoichiometry here in order to account for certain things. So we can, if you read through this, this is telling you that 1 mole of propane C3H8 is equal to negative 2044 kilojoules. That's what I'm showing here in my notes. 5 moles of O2, see where I'm getting it from, it's the coefficient, is negative 2044 kilojoules. 3 moles, 4 moles. And so we can develop equivalent statements, and then from there we can develop conversion factors to help us make a stoichiometric conversion. So if I asked you a question like how many moles of carbon dioxide are needed to give off 1,022 kilojoules of heat, well, I know if I'm giving off heat that it's losing heat, so that's why I put negative 1,022 kilojoules, and then notice my ratio. Negative 2,044 kilojoules equals 3 moles of carbon dioxide. Notice where I'm getting 3 moles of carbon dioxide, negative 2,044 kilojoules. And so that's how we're doing. If I were to say, and then, so if you did that calculation, you would get 1.5. If I did the same thing and wanted to know about, and unfortunately I wrote this down wrong, but I now see it, grading my own work, it would be, of O2, we have negative, if we had 1,022 kilojoules given off, we would know that we would have used 2.5 moles of O2 in order to get to that. All right, and we used a relationship between 5 moles of O2 and 2,044 kilojoules. So that's all I had there. I have another example problem if you want to look at that. If you still have time, push pause. Maybe you're trying to go to sleep. Just keep listening and you'll have no problem, I assure you. So what you're looking at here is calculate the heat in kilojoules associated with the complete reaction of NH3. Well, you should know that we're going to have to go from grams to moles. And so because we need to use our balanced equation, so we're going to need our handy dandy periodic table. In this lesson, I am not going to go over how to calculate molar mass for several reasons, but I will give the molar mass of NH3 here. You will need to calculate molar mass when necessary. It's just not something I'm showing in this video, as it is a easy first year chemistry objective. All right, so the molar mass of NH3, and I'll just write it down, molar mass of NH3 is equal to 17.03 grams per mole. All right, and so I'm just given that. You would have to calculate that. You do not have to show that calculation. But if you Google the calculation, make sure you know you're not going to get to Google it on a test. So we're going to start with our given of 155 grams of NH3. And make sure you're showing the unit and the substance on all of these. And then we're going to multiply that times using our molar mass to get to mole. So we're going to say that we have 17.03 grams of NH3. And notice we're not saying grams per mole. We're saying grams here in the denominator is equal to what? 1 mole of NH3. We're using the molar mass as a conversion factor. And then we're going to now use the stoichiometry of the equation. So we're looking at NH3. What's my coefficient of NH3? And you can see there it is 4. So we have 4 moles of NH3 is equal to, and what does this say here? negative 906 kilojoules. So it would be negative 906 kilojoules. Now, I ask you, is that an endothermic or exothermic reaction? That's right. That's right. It's negative. So it is an exothermic reaction. That's pretty good. Way to go there, champ. So here we're going to put this into our calculator. So we have 155. Let's go and plug this in. 155 times negative 906. And we're going to divide that by, let's see what that is. 155 negative 906, 17.03. And if you're using a calculator, you probably want to use parentheses for sure. Desmos is not super specific about it, but some calculators are. It messes up in their order of operations. And then the other one would be 4, right? And 4. So we'll plug that in. And what we get is negative 2,000 la-di-da-di-da-di joules. All right. And so, did I lose my work? I may have lost my work. Give me a second. My internet is a little slow. Okay, so let's go back over here. Oh yeah, I should have added my calculator. I kind of messed up by not doing that. Well, we'll do that again real quick. It's not a big deal. Yeah, anytime you leave, you should make sure that you hit add math. Otherwise, you might run into this problem. It's not a terrible problem, but it's not exactly awesome either. We'll just fix it real quick. But all right, and so this is equal to 1 mole of NH3, and of course you can always copy and paste NH3 if you find that horrible to type. I don't find it so horrible. And then we know that 4 moles of NH3, whoops, there we go, NH3 is equal to negative 906 kilojoules. And then now we can say this is equal to Control V, and we have our value, and we can say that's kilojoules. But we also need to make sure that we have the correct number of significant figures. Our given had 3 sig figs, so our answer should be 3 sig figs. So we would say negative 2,060 kilojoules. And there we would go. All right, and so there we go. And that takes that into account. All right, so sometimes if you go in and out, it fixes the sizing on that. Not a big deal. You would make sure you put your answer in here and your unit. Okay, so if we look at our rubric, we want to make sure we got everything in there. Stoichiometric setup. We did have a response. That's awesome. Stoichiometric setup is correct about all ratios are valid. Yeah, you're going to have to make sure you know your ratios are valid. You should know that molar mass has a gram to moles, and then you should know your ratio from your equation to the coefficient. And so those are what I'm looking for there. You're making sure that you have the substance. It not only says grams, but it says NH3, so we know what we're talking about. Why don't we say gram or kilojoules of NH3? Well, it's now transferred. That's now talking about energy. You can't have energy of NH3, so it just remains kilojoules. But you can have moles of NH3. You can count the number of atoms or molecules of NH3. All right, and so that's how you would do that. And then just one more, just to make you happy. It says how many grams of O2 will be consumed when 155 grams of NH3 completely reacts, and then use your answer. Maybe I need to know how to spell answer from the previous question to solve. So what you're going to do here is we're going to use our answer of negative 2,060 kilojoules, and then we're going to go to the mass of O2. So let's do that real quick. So we got negative 2,060 kilojoules, and we want to go into mass of oxygen. And so we know we're going to use our conversion factor, negative 906 kilojoules. Sorry, negative 906 kilojoules is equal to how many moles of oxygen? Hey, that's right, champ. 5 moles of oxygen. All right, and then we just have to go from moles of oxygen to grams of oxygen, and that's a pretty easy one because oxygen has a molar mass of 16, so 16 times 2 is 32 grams per mole, right? So 32 grams of oxygen. And now we have to say of oxygen, right? So notice I went from kilojoules, now I'm saying moles of O2, not just moles, but moles of O2, because I want to be specific about what I'm talking about. And so now we plug this into our calculator. We don't want to make that same mistake we made last time, so I'm going to hit add math. Might even go ahead and shrink this. But I definitely don't want to leave that open and then it lose it again. So negative 2060, and then we're going to say times 5 times 32. And then because I didn't put a parentheses around that, I'm just going to say answer divided by what is in my denominator, negative 906. So negative 906. And sure enough, I get this value here. And I want you to notice that, whoops, that didn't give me what I wanted. There we go. That gives me what I want. I want you to notice that we have a positive value. And why is it important that we have a positive value? Because we can't have a negative mass. So we have to say that it is positive, but it came out positive because we had negative and negative. And so how many sig figs can we have? 3. So we have 1, 2, 3, 363.7. That 0.7 will round that up to a 4. So we have 364 grams of oxygen. And so with all of that, you now got the lecture for October 12th. And hopefully you are well served in making sure that you know how to perform these calculations, just in case we have a quiz or something of that nature that goes over this reading and this very, very simple exercise of reading notes and all that good stuff. So you have some examples to look at. You have examples from the text, and you have some highlights from the text that I wanted you to look at. So anyway, I hope this video helped. Thank you for watching. Please like and subscribe.